Now that we've given you an overview of Android concurrency frameworks and motivated why we need them and what constraints they address with the Android system, let's go ahead and zoom in on the Android AsyncTask framework. And I'll start by giving you an overview of the capabilities that the Android AsyncTask framework provides. In a nutshell, what it does is it allows apps to perform background operations and publish results on the user interface thread without requiring application developers to explicitly manipulate threads, handlers, messages, or runnables. So if you think about the various elements and classes we talked about before in the Hammer framework, I talked about things like the looper and messages and message queue and handler and runnables and so on, and of course threads. It's really not clear from reading the Android documentation that these classes have anything to do with each other. They appear at first glance to just be disconnected classes or very loosely connected classes. Now this kind of complexity, this kind of flexibility works well for simple concurrency use cases. For example, if you have a background thread that does some computation, maybe blocks for a while, and then posts a runnable with a result to the user interface thread, and then the user interface thread takes that runnable and dispatches the run hook method of the runnable in the context of the UI thread to update the GUI. Those kind of things work perfectly well, getting information from the background thread to the user interface thread. However, it's important to realize that there are various drawbacks to the Hammer concurrency framework. One issue, of course, is you have to understand patterns to use this framework effectively. You have to understand the active object pattern, you have to understand the command processor pattern, and so on. And while these are not the world's most complicated patterns, it takes some time to get all the pieces in place and to understand how the various parts fit together. It's also a bit tedious and error-prone to use. For example, applications have to understand how to manage the life cycle of messages, which is a little tricky in the Hammer framework. So if you have a message that's sent from one thread to another, or you post a runnable, those things get called back, and you have to keep track of the lifetime of the message and so on. And it just gets a bit unwieldy if you're not careful. Another problem is that all communication between threads has to be explicitly programmed. If you want to pass a message from one place to another, you have to write the code to do that. You have to keep track of it. You have to make sure that the threads are up and running and so on and so forth. So it gets a little bit tricky to program. Another dimension of this is if you want to do certain things before giving the work to a background thread in the foreground thread, and then after the background thread is done, you want to do some additional work in the foreground thread, you have to explicitly program this. A good example of this would be starting and stopping a progress dialog box. So you'd really like that to start in the user interface thread before things start to run in the background, and then after the processing is done, you'd like to tear down that dialog box. And those teardown operations, those creation and teardown operations, must be done in the user interface thread. And yet another challenge is you can't scale up the performance of the Hammer framework transparently. You have to write thread pools, you have to manage the processing, you have to pass things back and forth. So it gets, once again, it's kind of tedious and error-prone to use. In contrast, the classes in the AsyncTask framework are more strongly connected. They're not just sort of loosely connected. You have to put the pieces together yourself by knowing these patterns. Instead, they're packaged together for you by the Android framework in the context of the AsyncTask class. And one of the nice things about this is that all the low-level details going on with the AsyncTask framework internals are all hidden by use of the facade pattern. So all you see as an outside programmer is just the AsyncTask object, and you tell it to execute some work. That's all you have to see from an end user point of view. Internally, the AsyncTask framework behind that facade is a complicated framework that does all kinds of things. It's got an executor pool, it's got a handler, it's got a future task, it's got a bunch of hook methods that it calls back, but you don't have to know all the internals, you just have to know how the interfaces work. So as a consequence, it yields a nice small surface area where you just have to know kind of the public interface rather than the implementation details. And it allows you to focus on the what, not the how. So this is that classic abstraction metaphor I like to use where you only have to see the tip of the iceberg and all the complexity is covered underneath the surface. As a consequence, it's possible to run various tasks concurrently without requiring the application developers to directly manipulate threads, handlers, messages, or runnables, unlike the Hammer framework, where you have to explicitly deal with those various kinds of entities as first-class citizens in the abstraction. There's a number of really cool hook methods that can be used to automatically perform pre-processing, in other words, in the user interface thread, post-processing, in other words, after the computation is done in the user interface thread, as well as interesting communication that can take place back and forth between a background thread and the user interface thread as the computations take place. So all of these things are automatically handled for you, and it's hidden for you with the template method pattern. Another cool thing about the AsyncTask framework is you can scale up its performance transparently. And that's because under the hood, it contains a pool of threads that can be specified by programmers. You can either use what comes out of the box via various policies you can give it in a black box-like way, or you can explicitly give it the thread pool that you want it to use. Not surprisingly, this thread pool can be implemented using the Java Executor framework. So we had talked before about the Executor service, we talked about thread pool Executor, we talked about the fork join pool, we talked about cached thread pools, we talked about fixed size thread pools. All of those mechanisms can either be used out of the box or customized in order to provide specialized thread pool semantics for the AsyncTask framework. So that's really cool, much more powerful than what you would get were you to try to program with the handlers, messages, and runnables or Hammer framework directly. So that's the end of the overview of the AsyncTask framework. Of course, we will go into much more detail shortly about the various methods it provides and show you some examples of how to apply it in practice.